Welcome to today's video. We'll be solving problem number 1518, water bottles, a fascinating challenge that tests both your logical thinking and problem-solving skills. Stick around as we break it down and explore the best approaches to tackle this problem step by step. Let's dive in. In this problem, you are given a certain number of full water bottles, represented by the variable number bottles. You can drink one bottle at a time, and after drinking, the empty bottle is left over. These empty bottles can be exchanged for new full bottles, with the condition that you need a specific number of empty bottles, defined by the variable number exchange, to get one full bottle in return. Your task is to calculate the maximum number of water bottles you can drink, considering both the initial bottles you start with and the additional bottles you can obtain through the exchange process. The input consists of two integers, number bottles, representing the starting number of full bottles, and number exchange, which is the number of empty bottles required for one exchange. The output should be a single integer indicating the total number of bottles you can consume. Here's an example to help us understand the problem better. Suppose you start with number bottles equal to 9 and number exchange equal to 3. First, you drink all 9 bottles, leaving you with 9 empty bottles. Since it takes 3 empty bottles to exchange for one full bottle, you can exchange these 9 empty bottles for 3 full bottles. After drinking those 3 bottles, you're left with 3 more empty bottles. You can exchange these 3 empty bottles for one additional full bottle. Once you drink this final bottle, you are left with just one empty bottle, which is not enough for another exchange. So in total, you have consumed 9 bottles from the start, 3 from the first exchange, and 1 from the second exchange, giving a maximum total of 13 bottles. Now let's look at another example with number bottles equal to 15 and number exchange equal to 4. You begin by drinking all 15 bottles, leaving you with 15 empty bottles. Since it takes 4 empty bottles to exchange for one full bottle, you can exchange 15 empty bottles for 3 full bottles, with 3 empty bottles left over. After drinking these 3 new bottles, you now have 6 empty bottles in total, 3 from the previous leftover and 3 from the bottles you just consumed. Exchanging 6 empty bottles gives you one additional full bottle, with 2 empty bottles remaining. You drink this final bottle, leaving you with 3 empty bottles, which is still not enough for another exchange. Adding it all up, you have consumed 15 bottles initially, 3 from the first exchange, and 1 from the second exchange, for a total of 19 bottles. In the third example, you start with number bottles equal to 5 and number exchange equal to 5. First, drink all 5 bottles, leaving you with 5 empty bottles. Since exactly 5 empty bottles are required for an exchange, you can exchange them for one full bottle. After drinking this new bottle, you are left with one empty bottle, which is not enough for another exchange. So in this scenario, you drink 5 bottles initially and 1 from the exchange, for a total of 6 bottles consumed. This example demonstrates that the number of bottles you can drink depends heavily on the exchange rate and how many empty bottles remain after each exchange. Now, let's consider the constraints and edge cases. The problem specifies that the number of starting bottles, number bottles, can range from 1 up to 10,000, and the exchange rate, number exchange, can range from 2 to 10,000. For edge cases, if number bottles is 1 and number exchange is 2, you can only drink one bottle since you don't have enough empty bottles for an exchange. Another edge case involves large input values, where the solution must handle many iterations efficiently to compute the result. Additionally, if number bottles is an exact multiple of number exchange, the process ends cleanly without any leftover bottles. Finally, when number exchange is very small, such as 2, frequent exchanges are possible, allowing for a higher total number of bottles consumed. These scenarios highlight the importance of carefully analyzing the exchange process to ensure accurate results. To solve the water bottles problem, one intuitive approach is to simulate the process step by step, often referred to as the brute force approach. You begin with the total number of full bottles, represented by number bottles. Each time you drink a bottle, you increase the count of empty bottles. Once the number of empty bottles reaches or exceeds the exchange rate, number exchange, you convert those empty bottles into new full bottles. This process repeats until the number of empty bottles is too small to make another exchange. By summing up all the full bottles consumed during this process, you get the solution. Now, key observations here are that each exchange effectively adds more full bottles, which makes this an iterative process, and the simulation naturally terminates when you can no longer make an exchange. This approach has a linear time complexity, O(n), where n represents the total number of bottles consumed, since each iteration decreases the number of exchanges you can perform. Space complexity is constant, O(1), because we only track the empty bottles and the total count. While this method is simple to implement and easy to understand, it does have some trade-offs, like potentially redundant calculations when dealing with larger inputs. An alternative method is the mathematical approach, which avoids the need for simulation by directly calculating the total number of bottles consumed using a formula. The idea here is to break the problem down into its mathematical foundation. Each exchange of number exchange empty bottles gives one additional full bottle, so the total number of bottles consumed is simply the initial number of bottles plus the additional bottles obtained through exchanges. Using integer division helps determine how many full bottles can be obtained from the exchanges, while the modulo operation calculates the leftover empty bottles. The steps involve starting with the initial count of full bottles, repeatedly calculating new full bottles by dividing the number of empty bottles by number exchange, and updating the leftover empty bottles. This process stops as soon as the number of empty bottles becomes less than number exchange. This approach is much more efficient, with a logarithmic time complexity, log, number bottles, since the number of bottles decreases geometrically with each iteration. Space complexity remains constant, O(1), as no extra data structures are needed. While it is slightly more complex to implement than brute force, it eliminates unnecessary iterations and is computationally optimized. The mathematical approach stands out as the preferred solution due to its efficiency, especially when working with large inputs. By leveraging integer division and modulo operations, we can directly compute the total number of exchanges without simulating each step. This makes the solution both faster and cleaner. Although the brute force approach is easier to conceptualize, its iterative nature can lead to inefficiencies when the input values for number bottles and number exchange are large. The key insight that makes the mathematical approach so effective is recognizing that the problem boils down to a sequence of exchanges. By calculating the next set of full bottles and leftover empty bottles in constant time for each iteration, we avoid redundant computations entirely. This makes the mathematical approach not only elegant but also the optimal strategy for solving the problem, as it minimizes computation while still guaranteeing correct results. To solve this problem, we aim to determine the maximum number of drinks you can consume by drinking and exchanging bottles. We start with an initial number of full bottles, represented by number bottles, and a given number of empty bottles required for an exchange, called number exchange. The approach begins with initialization. We set the number of full bottles to number bottles and start with 0 empty bottles. Additionally, we introduce a counter, total drinks, to keep track of how many bottles we've consumed in total. Initially, this counter is set to 0. From here, we consume the full bottles. For every full bottle, we increment total drinks by 1 since each bottle provides 1 drink. After consuming these bottles, we add the same number to the count of empty bottles, as each consumed bottle leaves behind an empty one. Then, the count of full bottles is reset to 0 because they have been consumed, and we prepare for the next step in the process. Next, we focus on exchanging the empty bottles for new full ones. After drinking, we check whether the number of empty bottles is at least as many as number exchange. If it is, we calculate how many new full bottles can be obtained using integer division, empty bottles / number exchange. This represents the maximum number of full bottles we can get from the available empty bottles. Any leftover bottles that couldn't be exchanged are computed using the modulus operator, empty bottles % number exchange, and these are added back to the empty bottle count. The total number of empty bottles is then updated to reflect this new count. We repeat this process of drinking and exchanging until the number of empty bottles becomes less than number exchange, at which point no further exchanges are possible. Finally, when the process ends, the value stored in total drinks gives us the maximum number of drinks we were able to consume during this entire process. The solution to this problem relies on a step-by-step simulation of the drinking and exchanging process. By simulating each step, we ensure that the logic mirrors the real-world scenario described in the problem. This approach is efficient because, with each cycle of exchanges, the number of full bottles decreases significantly, following a geometric progression. As a result, the algorithm completes in logarithmic time with respect to the initial number of bottles, or O, log, number bottles. It's also important to consider edge cases. For example, when number bottles is less than number exchange, no exchanges are possible, and the total drinks will simply equal the initial number of bottles. On the other hand, if number exchange is 1, it would theoretically allow infinite exchanges, though such a scenario is not practical and would likely be invalid in real-world problems. These insights help us understand the algorithm's behavior under different conditions. The algorithm uses only a few simple data structures to achieve its goal. Specifically, it relies on counters to track critical values. The total drinks counter keeps a cumulative record of all the drinks consumed throughout the process. Meanwhile, the empty bottles counter tracks the number of empty bottles available at any given time for potential exchanges. Both of these are simple integer variables, which are sufficient for solving this problem. Importantly, no complex data structures like lists, queues, or hash tables are needed. This minimalistic approach ensures the solution remains efficient and easy to implement while still capturing the essential mechanics of the problem. The key operations in the algorithm revolve around 3 main steps. First, when drinking bottles, the total number of drinks is incremented by the count of full bottles currently available. Simultaneously, the consumed bottles are added to the empty bottles variable to ensure an accurate tally of empty resources. Second, during the exchange step, we use integer division to calculate the number of new full bottles we can obtain and use the modulus operator to determine any leftover empty bottles. This approach ensures both precision and efficiency in managing the bottle counts. Finally, the process terminates when the number of empty bottles falls below number exchange, since further exchanges would no longer be possible. These operations work together to simulate the problem efficiently while adhering to the constraints. To illustrate the algorithm, let's walk through an example where number bottles is 9 and number exchange is 3. Initially, we have 9 full bottles, 0 empty bottles, and a total drink count of 0. In the first round, we drink all 9 bottles, bringing the total drinks to 9, and we now have 9 empty bottles. These empty bottles are exchanged for 3 new full bottles, leaving no leftover empties. In the second round, we drink the 3 new bottles, increasing the total drinks to 12, and we now have 3 empty bottles. Exchanging these gives us 1 full bottle and no leftover empties. In the third and final round, we drink the last bottle, bringing the total drinks to 13, and are left with 1 empty bottle. Since 1 is less than the exchange requirement of 3, no further exchanges are possible, and the process ends. The output of the example is 13, representing the maximum number of drinks consumed. Let's analyze the complexity of the algorithm. The time complexity is O, log, number bottles, because the number of full bottles decreases significantly with each exchange, following a logarithmic progression. The space complexity is O(1), since the solution only utilizes a few integer variables, such as total drinks and empty bottles, regardless of the input size. This makes the approach both time-efficient and memory-efficient, making it well-suited for this type of problem. This solution aims to calculate the maximum number of drinks you can consume by drinking water bottles and exchanging the empty ones for new full bottles. Here's how the code works. 1. Initialization. The function starts by initializing total drinks to 0, to track the total drinks consumed, and empty bottles to 0, to track the number of empty bottles available for exchange. 2. Main loop. The while loop continues as long as there are full bottles, number bottles 0. This ensures that all available full bottles are consumed, and exchanges are made whenever possible. Consume full bottles, add number bottles, current full bottles, to total drinks to reflect the number of bottles consumed in this iteration. Update empty bottles, add the emptied bottles from the current consumption to empty bottles. 3. Exchange bottles, using integer division, //, calculate the number of new full bottles that can be obtained by exchanging the empty bottles. Update number bottles with this value. Any leftover empty bottles, not sufficient for another exchange, are updated in empty bottles using the modulus operator, %. For termination, the loop ends when no more exchanges are possible, i.e., number bottles becomes 0. At this point, the total drinks consumed, total drinks, is returned as the result. This implementation handles edge cases such as when number bottles is initially 0, no drinks can be consumed, or when number exchange is greater than number bottles, no exchanges can be made. The algorithm efficiently simulates the drinking and exchange process, ensuring correctness and clarity. This is the Java implementation of the water bottles problem, which follows the same logic as the provided Python solution. The method number water bottles calculates the total number of drinks possible by repeatedly exchanging empty bottles for new full ones. Key differences include explicit type declarations and the use of integer division and modulus operations for the exchange logic. The solution is encapsulated within a solution class as per Java conventions for LeetCode submissions. Here we have the first example where the number of bottles is 9, and the exchange rate is 3. Initially, we start with 9 full bottles, no empty bottles, and the total drinks consumed is 0. In the first iteration, we drink all 9 bottles, so the total drinks become 9. These 9 empty bottles can now be used for exchange. Since the exchange rate is 3, we can trade them for 3 new full bottles. After the exchange, there are no remaining empty bottles left over. Now, in the second iteration, we drink all 3 of the full bottles we just obtained. This increases our total drinks to 12. The 3 empty bottles from this round are added to our count of empty bottles. Using the exchange rate of 3, we trade these 3 empty bottles for 1 new full bottle, leaving no empty bottles remaining. In the third iteration, we drink this last full bottle, bringing the total drinks to 13. The empty bottle left over is not enough for another exchange, so we stop here. The final total number of drinks is 13. Next, let's look at the second example where we start with 15 bottles and an exchange rate of 4. Initially, we have 15 full bottles, no empty bottles, and the total drinks consumed is 0. In the first iteration, we drink all 15 bottles, so the total drinks become 15. These 15 empty bottles can now be used for exchange. With an exchange rate of 4, we can trade them for 3 new full bottles, leaving 3 empty bottles remaining after the exchange. In the second iteration, we drink all 3 of the new full bottles. This increases the total drinks to 18. The 3 empty bottles from this round are added to the 3 leftover empty bottles from earlier, making a total of 6 empty bottles. Using the exchange rate of 4, we trade these 6 bottles for 1 new full bottle, with 2 empty bottles remaining after the exchange. In the third iteration, we drink that last full bottle, bringing the total drinks to 19. The 1 empty bottle from this round, combined with the 2 leftover empty bottles, is not enough for another exchange. Thus, the process ends here with a final total of 19 drinks. Now let's move to the third example, where we start with 5 bottles and an exchange rate of 5. Initially, there are 5 full bottles, no empty bottles, and the total drinks consumed is 0. In the first iteration, we drink all 5 bottles, so the total drinks become 5. These 5 empty bottles are used for exchange. Since the exchange rate is 5, we can trade them for 1 new full bottle, leaving no empty bottles remaining after the exchange. In the second iteration, we drink the last full bottle, increasing the total drinks to 6. The empty bottle left over is not enough for another exchange, so the process ends here. The final total number of drinks for this example is 6. This concludes the walkthrough of the problem, showing how we iteratively calculate the total number of drinks by exchanging empty bottles until no more exchanges are possible. To analyze the time complexity of this algorithm, we focus on the while loop, which determines how many iterations are required to calculate the total number of water bottles that can be consumed. The key observation here is that in each iteration, the number of new full bottles obtained decreases geometrically, as it depends on dividing the number of empty bottles by the exchange rate, number exchange. Initially, we start with the given number of full bottles, number bottles. Then, at each step, the number of new bottles is derived from the quotient of empty bottles divided by number exchange, where empty bottles accumulates over time. This process continues until the number of full bottles becomes 0. Because the number of full bottles reduces by a factor of approximately number exchange in each step, the total number of iterations is proportional to the logarithm of the initial number bottles with base number exchange. In terms of big O notation, this simplifies to O log number bottles. Now looking at the overall time complexity, since the operations inside the loop, such as addition, division, and modulus each take constant time, or O1, and the loop itself runs O log number bottles times, the cumulative time complexity remains O log number bottles. Shifting to space complexity, the algorithm maintains only a fixed number of variables throughout its execution. These include total drinks, empty bottles, and number bottles, all of which require constant space. No additional data structures are introduced, meaning the memory usage does not grow with the size of the input. When we break down the memory usage, each variable total drinks, empty bottles, and number bottles requires O1 space. Therefore, the total space complexity is O1. The overall space complexity of this algorithm is constant, or O1, as we've seen. This efficiency becomes particularly evident when we compare it to a naive approach. A brute force method might involve explicitly simulating the process of drinking and exchanging bottles step by step, possibly using additional data structures to track the state of bottles or to count each exchange explicitly. While this naive approach would still involve a geometric reduction in the number of bottles, leading to the same time complexity of O log number bottles, the added use of data structures could result in a space complexity of O(n) or higher, depending on the implementation. By contrast, the current optimized approach avoids these inefficiencies, achieving both optimal time complexity of O log number bottles and space complexity of O1. The logarithmic time complexity can be mathematically justified by examining how the number of full bottles decreases with each iteration. Specifically, at each step, number bottles is reduced by a factor determined by number exchange. After k iterations, the number of bottles can be approximated as number bottles / number exchange (k). The loop terminates when the number of bottles drops below 1, which occurs when k is proportional to log_base, number exchange, number bottles. In big O terms, this simplifies to O log number bottles. Regarding space complexity, no additional data structures are used, and only a fixed number of variables are maintained throughout the algorithm. This consistent use of memory confirms the constant space complexity of O1, making the algorithm both time and space efficient. When tackling this problem, there are a few common mistakes that can trip you up. First, forgetting to handle edge cases is a frequent issue. For example, if number bottles is 0, there are no bottles to drink from, and if number exchange is 1, you could end up with an infinite loop because you can keep exchanging indefinitely. It's important to always consider boundary conditions to ensure your solution doesn't fail in these scenarios. Another common pitfall is off-by-one errors. This happens when you miscount the bottles or exchanges, such as forgetting to include the bottles received during the final exchange. These small oversights can lead to incorrect totals. Additionally, a naive simulation approach can be inefficient when the number of bottles is large. Instead of iterating step by step, using a mathematical formula to calculate the total directly is often the better choice. Lastly, overcomplicating the logic with unnecessary variables or loops can make your solution harder to understand and debug. Simplifying your approach ensures clarity and reduces the likelihood of introducing bugs. Not accounting for remainders is another critical mistake to avoid. When you exchange empty bottles, any remainder bottles should be added back into the count. Neglecting this can result in underestimating the total number of bottles consumed. Now, in an interview setting, this problem is often used to assess your ability to balance simulation with optimization. While brute force solutions work, interviewers typically prefer a more optimized mathematical approach. Always be prepared to analyze edge cases carefully and ask clarifying questions, especially around scenarios where number bottles or number exchange could be 0 or 1. Time complexity is another key consideration. A mathematical solution offers O1 complexity, making it much faster than a simulation, which could take O(n) in the worst case. Throughout your explanation, remember to clearly communicate your thought process, particularly when transitioning from simulation to an optimized approach. Explain why optimization is necessary and how it improves your solution. This problem also has connections to other related problems that test similar concepts. For instance, LeetCode 134, gas station, involves balancing resources and optimizing under constraints, much like the water bottle exchanges. Another example is LeetCode 877, stone game, which focuses on strategic resource allocation. Similarly, LeetCode 881, Boats to Save People, revolves around optimizing the use of limited resources, in this case, boats, to achieve a goal efficiently. Lastly, LeetCode 1221, Split a String in Balanced Strings, emphasizes counting and balancing logic under constraints. Exploring these problems can help deepen your understanding of strategies like resource balancing and optimization, which are crucial for tackling challenges like the water bottles problem. There are several approaches you can take to solve this problem, each with its own trade-offs. The first is a brute force simulation, where you simulate the process step by step, counting the bottles consumed and tracking the empty bottles. This method is straightforward to implement, but it can become slow when the inputs are large. A more efficient alternative is the mathematical approach. Here, you derive a formula to calculate the total number of bottles consumed, including those obtained through exchanges. This method is much faster, with a time complexity of 1, but it requires careful reasoning to ensure the formula is accurate. There's also a hybrid approach, which combines the two methods. You can use simulation for smaller inputs and switch to the mathematical formula for larger ones. This balances ease of implementation with efficiency, though it does add some complexity to your solution. Each of these approaches has its own strengths, so choosing the right one depends on the problem constraints and your comfort level with optimization. That's a wrap. Today, we tackled problem number 1518, water bottles, and explored how to simulate the process to maximize the solution. Remember, practice makes perfect, so keep working on similar problems to sharpen your skills. Thanks for tuning in. Make sure to like, comment, and subscribe for more problem-solving content. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!